I will explain now how to identify models of special kind of robotics hands, which are underactuated adaptive robotic hands, which are typically made of soft materials, and they pose a special kind of challenge where the methods that we explained before cannot work easily on this kind of hands. So this is a project in collaboration with Aaron Dollar at Yale University, where he's leading this project, which is called the Open Hand Project at Yale. And the idea there is to develop cheap, low-cost hands that can be made of 3D printed parts and often compliant parts, and that can be used for grasping and manipulating objects. These are open designs, so anybody can make this in their own lab if they have 3D printer, basically. So underactuated hands are great because they can passively adapt to objects. They provide good grasping performance without having to sense. So just because of their flexibility, they are also low cost, and they have very compact design. However, they have special challenge. They are very difficult to model analytically and to control. They are notoriously challenging for that, and they have very high uncertainty due to the use of soft materials. Soft materials are their mechanics is really difficult to model analytically. So this is the kind of tasks that you want to do here. We're going to be focusing on in-hand manipulation, where we have an object in the hand, and then we'll be trying to move it from one configuration to the next configuration, or want, for example, to track certain trajectory, like what we are seeing here. So this is two-fingered robot that we had in our lab, and then we were trying to move it by following a certain predefined shape. And what we notice in general is that regardless of how good is our simulator, we'll always notice difference between what happens when we execute the trajectory versus what we predict on simulation. And so one way to solve this problem is to do learning, basically, and to learn a model of how the hand works. So we built a setup where we can put an object and then collect the motion of the object and then predict how it's moving, build an analytical model, statistical model for how the object is moving. And then we made this system fully autonomous. So we have just dual arm robot where on one hand we have, so I'm going to replay this a little bit. So we have two arms and then an object, and it's attached to string. And this system was working like for 24 hours non-stop, just grasping an object, playing with it autonomously, and then whenever it falls, we detect from vision that it fell down, and then we can pull it up again, and then repeat the same thing. We did this with different shapes of objects. So we collected a lot of data, and this is published in R4DC this year, and data is publicly available for people who want to use it to learn dynamics of this kind of soft underactuated hands. So the first method that we used for modeling the dynamics is a Gaussian process, where as an input we have state at time t, action at time t, and the output is state at time t plus 1. However, we notice that if we use a kernel in the Gaussian process, and the kernel is just a Euclidean distance or exponential of the Euclidean distance, it didn't work very well. So we thought of that the data itself actually lives in low-dimensional manifold. So if you take an object and you start moving it, and you try to plot the state space, it's not going to be full dimensional, but it's going to be living in some kind of surface. So we used the manifold distance as a way for measuring similarities between data points. And the idea that we used here is called diffusion maps. So people who are familiar with heat equations, they know this idea. And this is a comparison between the performance that we get using Euclidean distance, Gaussian process with Euclidean distance, and we are trying to predict next state, versus what we get when we use manifold distance. So it turned out to be important. And we couldn't use easily neural networks at the beginning because we didn't have a lot of data, and the Gaussian process works much better when you have very little data points. And the blue path there is the predicted path in simulation, and the yellow path is the executed path. And you can see that when we use manifold distance and we learn the dynamics, with Gaussian process, we can get almost perfect overlap or perfect match between the predicted path and the actual tracked path when we execute the same sequence of actions in the real world. So this is the kind of experiments that we did in this work. We put a lot of objects, and then we're trying to predict how they move, and then we execute the loads that we apply on the actuators, and then observe how the object move, the object inside between fingers, and then we report this error. So that was published at ICRA 2019. I didn't put the reference here, I think. Okay. Then next step is we start looking into using these kind of models to perform tasks. For example, we want to follow some trajectory, or we do peg in the hole task. And in order to do that, you need to have some kind of planning. But these models are not very certain, so you cannot come up with a 100% deterministic plan. What you need to do is to do belief space planning. So basically, you build the tree from start configuration to the goal configuration, where each node in this tree doesn't correspond to a single state, but actually it corresponds to a set of possible states. And you will be computing the probability that this set of states will be colliding with an object based on how many samples we have inside this state, for example, how many particles we have there. And then if a branch leads to collision with high probability, then that branch can be pruned, that can be avoided, and so on. And we use this idea of belief space planning using the model that we learned on the robot to perform interesting tasks such as inserting an object inside the hole. And this is done open loop, so there is no sense in being done. We just plan offline, and then we run the plan directly in physical robot. So it's very sensitive to modeling errors. And on the right hand is what we get when we do the probabilistic robust planner, and on the left hand is what we get with standard deterministic planner. And they are both using a model that was learned from data, the Gaussian process model. And this was published at ISRR last year. So later on, we replaced the Gaussian process with the Bayesian neural network, or just neural network if you want. And the input there is the state at time t, the action at time t, the data, and then we predict the state at time t plus 1. However, we noticed something, which is these diminishing returns. So the accuracy of the neural network achieves a certain plateau, a certain level. And then after that, regardless how much data you put into it, it remains almost the same constant. So basically, you can spend basic 30% of the data will get the network into 90% accuracy, and then the rest of the data will not improve it by 1%. And this is a well-known problem, diminishing returns. So we thought of the following: instead of like wasting all the data into fine-tuning the neural network, hardly, and it doesn't improve really, let's split the data and use a lot of data for training the transition model directly, as we did, and then save a big part of the data for training the second neural network that we're going to call the Critic Network. And the job of the Critic Network is this. You take as input the state at time t, the action at time t, and then it's just neural network parallel to the dynamics or transition neural network. The difference is that the output of the Critic Network is the error that we think the transition neural network is going to make. So basically what we are trying to learn is which state space, which regions in state space and which actions the neural network tends to make more errors in. So basically, where does the neural network fail the most at making accurate predictions? And this seems like easy to evaluate because there is kind of systematic errors. So basically, there is like kind of a pattern in the way the network makes errors. There are certain regions, like for example, when you are close to the boundary, to the edge, where often there is less data, and neural network tends to make more errors there. There are also regions where there is a lot of noise, and because the system is very stochastic there, and the neural network tends to make a lot of errors there. So it's easy to train a second neural network that keeps track of the original neural network. It's kind of watching the original neural network and learning where it fails the most. And then we're going to incorporate that into the planner. So if you take like just regular tree planner, you come up with the tree starting from initial configuration to goal configuration, and then you can come up with what you think is the optimal path. But if you call and transitions here in this tree are all given by the dynamics neural network. That's how we connect one point of the tree to the next point. But if you call this critic neural network, it's going to reveal parts where we tend to make a lot of errors, where the neural network cannot be trusted there. Okay, so the dynamics neural network cannot be trusted in these regions where we have this high error, red regions. So if you incorporate this as part of the cost into the planner, the regions where we we tend to make a lot of errors using the dynamics network, then we're going to get a different path that it's not the really shortest path, but actually it's going to avoid regions where the transition neural network cannot be trusted with its predictions there. It tends to make a lot of errors there. And actually that worked pretty well, and when we compare the two versions, and this is an experiment where we take an object and we try to insert it into goal configuration while avoiding obstacles. So this is the same experiment from top view. We want to move an object to goal configuration and we want to avoid obstacles, and this is what we get when we use this idea of critic neural network. So last thing I want to explain here about identifying models for this kind of adaptive underactuated hands is the idea of transfer learning. So it did take a lot of data, a lot of time to learn a model for single hand. It took us something like 24 hours non-stop of the robot just playing with the objects in order to learn how this hand works. And then we built, these hands are really easy and cheap to make, so we made quickly a second hand and we went to use it again for doing the same tasks. The problem is that we didn't want to repeat the entire data collection of the new hand. That would be a lot of work. We wanted to take the model that we learned from the original hand and transfer it directly to the second hand, and this is called transfer learning. So we wanted to learn only the difference between their dynamics and tune the dynamics to be able to use it on the second hand, the red hand. So we have this gap again between the predictions that we will be getting if we use the source hand versus what will be happening on the target hand. And the idea is to learn to model this difference, which is what we call transfer residual, the difference between the two at each time in the future, the difference between the corresponding states, the state that we get from the original hand versus the state that we get with second hand. And we want to learn just this difference and update it. So this is an idea that has been done before, but actually we developed it, and this residual can be learned by using a neural network, by the way, different neural network for just the residual. It could be very simple, it could be trained with very little data. So this is an idea that has been proposed before, but the difference is the way we are composing these residuals. So we found that actually the best way to compose these residuals is to do them in a cumulative way, such that you take the residual that you had in the previous step and then you add to it. So you take this residual here, you apply it to the next time step, and then you add to it a new residual. And this gives us the corrected position. By the way, the red black line here is the one that we get when we use directly the model, the neural network that we trained with the original hand. And the blue one is what we should be getting on second hand, and we are trying to learn the corrections, how to correct the trajectory that we get from the original hand to make it overlap with what we are getting with second hand. So basically we just accumulate these residuals, so we have sort of memory where we inherit the previous residuals, these two, put them here, and then we add a new residual, third one, and we get corrected pose, and that worked much better than just the usual approach of just learning residuals separately at each time step. Actually, we had also theoretical analysis why this works. It's related to Lyapunov exponent of the transferred system, and using this idea can bound that Lyapunov exponent, which corresponds actually to how unstable a chaotic system is. This is just numerical experiment of using actually the real data, where we want to predict. We collect a lot of data points, and then we run those actions into the model that we transferred, and we want to predict the final pose of the object after we execute these actions. So what this is showing is on the x dimension, what we have is how far is the goal from the start position, and how accurate on the y dimension is how accurate the predictions are. Of course, the further you put the goal, the more difficult it is to predict where the object is going to end up if it's trying to reach that goal, because it's as you add more time, the errors just keep accumulating. And this comparison with all different kinds of methods for doing this transfer learning. So there is a naive fine-tuning of neural networks that people usually do a lot, where they take the original neural network and then they just fine-tune it by using data from the second domain. We had also the recurrent residuals where we used the recurrent neural network. And actually the method that we proposed, which is the cumulative residuals, work the best. So you can see that the error drops more slowly as the goal move further from start position.